In this video, I want to show you that the Dirac Delta can have the following representation. So it is called representation, and I will try to explain to you in a second what that is. So let's start from this function, sine squared of t times x, and let's divide this by t times x squared. So only the variable x is squared here in the denominator, whereas t is not squared. And then we take the limit as t goes to infinity. We can show that this is equal to the Dirac delta times a constant which is pi. So it's pi times the Dirac delta. Or if you want, you can put pi here in the denominator. But for the sake of convenience, I will just put it here to avoid writing a constant here in the denominator, but that is just a choice. Now we want to prove this kind of relation, and I would like to try to explain to you what the representation of the Dirac delta here is. As you might know from physics and also mathematics, the Dirac delta is not really a function. It's called a distribution. It's not a function because, you can think of that as a function, but it's a special function because it is equal to infinity at x equal to 0. So we represent it by using sometimes an arrow like this. So it's some kind of arrow to indicate that it's equal to infinity here, and then it is 0 when x is not equal to 0. So this is the function delta of x, quote unquote function. As I said, this is not a function, it is a distribution, but sometimes, to simplify this kind of terminology, it is conventionally called a function. But as I said, it is a distribution, and in particular, you can think of that as a limit, for example, of this kind of function here. So you can think of the following function. You have a rectangle around the origin, and you can call this function delta sub a of x, where this delta sub a is equal to a constant, which is 1 over a, when x is between minus a over 2 and a over 2. So this is a over 2 minus a over 2, whereas this is a over 2 here, this is x, and this height is 1 over a. Then you let a go to 0, right? And if you let a go to 0, this value will be infinity. When a is very, very small, it will go to infinity. And you can see that this interval is smaller and smaller as a becomes smaller and smaller. So at the end, you will get x equal to 0 from here. And also, let me tell you that the function delta a is 0 when x is not in this interval, so we can simply say otherwise. So outside of this interval, the function will be 0. And then you will obtain the Dirac delta from here as you let a go to 0. Another way to represent this delta, Dirac delta, is also by using this limit. And there are other functions that you can consider here, and it can be shown that the Dirac delta can be represented in different ways. Now we'll take care of this representation. I want to show you that this is indeed a good representation. Also, let me remind you the following property of the Dirac delta, the integral of delta x dx from minus infinity to infinity is equal to 1. So this is a property which should be satisfied, and if you recall, if you have a function f of x and you multiply it by delta of x, then this is equal to f of 0 delta of x. This is another simple property of the Dirac delta. Now, in this video, I want to show you that if you consider this limit, well, this function, when you think of t as very large, will be infinity when x is equal to 0, and it will be 0 when x is not equal to 0. So let's first show that the limit as t goes to infinity of sine squared of tx divided by t times x squared, well, this is 0 if x is not 0, and this is quite easy to show because in this case this denominator will become larger and larger, whereas the sine is an oscillating function which oscillates between -1 and 1, and the sine squared will oscillate between 0 and 1 actually, because it is squared, and therefore you can easily check that it will be 0 indeed if x is not equal to 0. But what happens if x is 0? Well, if x is equal to 0, even if t becomes larger and larger, this denominator will be 0. And also the argument of the sign will be 0. So you will get 0 over 0, which is an indeterminate form. But in the limit, if you think of this argument here as very, very small, and it will be small even if t is very large because we set x equal to 0. So you can think of x as approaching the 0 much faster than t approaches infinity. And therefore, the sign of tx can be written as t times x. Then you have to square it because you have the sine squared of that, and you divide by tx squared. Then you can simplify x squared on both, on both the denominator and the numerator, and therefore you get t squared over t. And this will be, of course, equal to t. And in the limit, as t goes to infinity, of course, this will be infinity, right? So this first part, which is a property of the Dirac delta, is satisfied. But we cannot say that this is equal to the Dirac delta, right? Because we know that it is 0 if x is not equal to 0, and it is infinity if x is equal to 0, but we don't know if the integral from minus infinity to infinity of this function, let's call it a function, so limit t goes to infinity of sine squared dx divided by tx squared dx, we don't know whether this is a finite result. So how do we relate it to the Dirac delta? Well, we can do it by calculating such an integral, and we have to show that this is equal to pi. And why is that? Well, you can see it from here. So if you integrate both sides from minus infinity to plus infinity, this will yield 1, whereas this will give us pi times 1, so we get pi. And therefore, this integral should give us pi. Anyway, if we prove this relation, then you can actually say that this function here, let's call it a function, even if it is not technically a function, will be equal to pi times the Dirac delta of x. And now let's try to calculate this integral here. Integral from minus infinity to plus infinity of sine squared of tx divided by tx squared dx. Now let's remove this limit. Let's not take into account that we want to take the limit. Now we can rewrite this formula like this. Integral from minus infinity to plus infinity. And now I'm rewriting sine squared of tx as 1 minus cosine of 2tx divided by 2. And then we also get tx squared integrate over dx. Now at this point we are going to evaluate this integral here by using a contour integral, so contour integration. Remember also that t will have to go to infinity, and the integral that we will associate with that one is the integral over the contour gamma that I will define in a moment, 1 minus e to the I 2tz divided by 2tz squared dz. I will evaluate it like this. Now we'll integrate over the following contour. Let me sketch it here. It's an anti-clockwise contour. We have the discontinuity z equal to 0 here. This is the real axis, so the real part of z, which is equal to x, and then here we have the imaginary part of z, which we usually set equal to y. It's just a notation. Then we have a small semicircumference here where rho is the radius of the semicircumference, and then we have the radius capital R for the larger semicircumference. And this is what I called gamma there. So this is the contour gamma. The integral is equal to 0 according to the residue theorem because there is no discontinuity inside this region. So the area enclosed by this curve, and I can split this curve into 4 different parts. So I have gamma 1, which goes from this point to this point. Then I have gamma 2, which is the smaller semicircumference. Gamma 3 goes from this point to this point, and then I have gamma 4, which is the larger semicircumference. And I will let rho go to 0 and capital R go to infinity. And the integral over gamma will be split into 4 different integrals, the integral over gamma 1, the integral over gamma 2, over gamma 3, and over gamma 4. So I have 4 different integrals, and I can put together the integrals over gamma 1 and gamma 3. So I can integrate over gamma 1 union gamma 3, and this will give us, when we set rho, so when we let rho go to 0 and capital R go to infinity, we will obtain the integral from minus infinity to infinity of 1 minus e to the I 2tx, because we are integrating over the real axis, and we divide by 2tx squared dx, like this. Then we have to integrate over gamma 2, and the integral over gamma 2 is equal to integral from pi to 0, so we are integrating over the angular variable. So here we set z equal to rho e to the I theta. So we are parameterizing the semicircumference like this, and then I have 1 minus e to the I 2t rho e to the I theta divided by 2t rho squared e to the I 2 theta, and then I have the differential of z, which is rho I e to the I theta d theta. And now I can simplify this a little bit. This is integral from pi to 0, 1 minus e to the I 2t rho e to the I theta divided by 2t rho squared e to the I. So actually I can simplify this rho squared with the rho here. So I have rho in the denominator, and then I have e to the I theta, because I can simplify it with e to the I theta. Then I have I d theta, like this. And then I can let rho go to 0. Remember that also t should go to infinity, so that's a different limit. Now set rho equal to 0, or actually let rho go to 0. We can rewrite this complex exponential as 1 plus I 2t rho e to the I theta. So this will simplify like this, integral from pi to 0 of minus I 2t rho e to the I theta divided by 2t rho e to the I theta times I d theta. Now I can simplify 2t with 2t, rho with rho, e to the I theta with e to the I theta, and then I have I times minus 1, so I will get 1, and then I have to integrate from pi to 0, so I get minus pi. This integral gives me minus pi. And then I have the integral over gamma 4, which can be written in a similar fashion, but in this case we have to replace z with capital R e to the I theta. So it will become equal to this integral here, but instead of integrating from pi to 0, we integrate from 0 to pi, because we are moving like this on the semicircumference. So the angular variable here is increasing from 0 to pi, whereas in the case of the semicircumference, of the smaller semicircumference, we are starting at this point and then we are moving like this. So the angular variable will start at pi and it will go to 0 here, right? So we go from 0 to pi and we have to replace little rho, so the rho with capital R. So we have 1 minus e to the I 2t capital R e to the I theta divided by 2t capital R e to the I theta I d theta, like this. And then let me rewrite it like this: integral from 0 to pi 1 minus e to the I 2t r cosine theta times e to the minus 2t capital R sine theta divided by 2t capital R e to the I theta times I d theta. And now we let capital R go to infinity. And in this case, you can see that this complex exponential is simply going to oscillate between minus 1 and 1. I mean, its real part is going to oscillate between minus 1 and 1, and the imaginary part as well. So the magnitude of this complex exponential is equal to 1. Whereas this is a real exponential, and R is going to go to infinity, and T is also going to go to infinity. And the sign of theta is positive because theta is between 0 and pi. So it is equal to 0 only at theta equal to 0 and at theta equal to pi. But inside this interval, this is going to be positive, greater than 0. And this real exponential is going to decay very fast. We also have r in the denominator, which is going to infinity. So it's quite easy to understand that when r goes to infinity, this integral will give me 0. So the result that we get from here is simply that the sum of these integrals, which coincides with this complex integral here, which we split into 4 different parts, or actually 3, because we have united the integral over gamma 1 with the integral over gamma 3. So we have put the two integrals together. Finally, we can say that this integral here is equal to pi, because this integral plus the integral over gamma 2, which is minus pi, is equal to 0. Therefore, we can put pi on the right. And since the integral over gamma 4 is equal to 0, we can simply say that the integral over gamma 1 union gamma 3 is equal to minus the integral over gamma 2. And the integral over gamma 2 is minus pi, so we get minus pi, which is pi, right? And now if we take the real part on both of these two sides, well, the only complex quantity is this one. So we can say that integral from minus infinity to infinity, 1 minus the cosine of 2tx divided by 2tx squared dx is equal to pi. And from here we also get another result, which is not what we are interested in, but it's integral from minus infinity to infinity of minus the sine of 2tx divided by 2tx squared dx equal to 0. We get this result as well. And from here, from this result, we can say that this integral here is also equal to pi, which is what we wanted to show. And it means that the integral from minus infinity to infinity of the limit as t goes to infinity of sine squared dx divided by tx squared dx, and we divide by pi here, this is equal to 1. And it means that this quantity is a function, quote unquote function. It is not really a function, because we said that this behaves like the Dirac delta. So this is a distribution, and it is exactly coincident with the Dirac delta. We know that from this integral here, since its integral over the real axis is equal to 1, and it behaves exactly like the Dirac delta, since it is equal to 0 if x is non-zero, and it is equal to infinity if x is equal to 0. It's exactly coincident with the Dirac delta, and we can see it from also this representation, since if we integrate this function here, delta a, and we can also set, so we can consider the limit as a goes to 0, which will make this function equal to the Dirac delta, delta of x, this quote-unquote function. And if we integrate from minus infinity to infinity dx, this is equal to the limit as a goes to 0 of the integral from minus a over 2 to a over 2 of 1 over a dx, because delta sub a is equal to 1 over a between minus a over 2 and a over 2 and 0 otherwise. So this is what we get. But what is this integral equal to? Well, this is simply 1 over a times a, which is equal to 1. So this is equal to 1. And when we consider this limit, we know that this function here becomes the Dirac delta, the delta function. So it will be 0 when x is non-zero, and it will be infinity when x is equal to 0. So it's a special function, but it is exactly coincident with this special function here. Not really this one, but this one divided by pi here, like this. And now we can say that this is the Dirac delta. We couldn't say it here because, well, this is infinity if x is equal to 0, and it is 0 if x is non-zero, but nobody tells me that this integral here should be 1, so the function is normalized. This is a normalization condition, which is fundamental to define the Dirac delta. Now let me conclude also by showing you another way of calculating the integrals that we have calculated here in this video. In particular, I want to show you another way of calculating, where is it? This integral below, this one here. Let me frame it. This integral here. I want to show you another way of calculating this integral, which allowed us to find the integral that we wanted to find in this lecture. So let me go below, and I want to show you a way which does not resort to complex calculus. In particular, I want to write down the integral from minus infinity to plus infinity of the limit as t goes to infinity of 1 minus exponential to the I 2tx divided by 2tx squared dx. Now, since we have the limit as t goes to infinity, we know that this function here, when t is very, very large, this denominator will become larger and larger if x is not equal to 0. So if x is not equal to 0 and t is very, very large, this function will be oscillating and the denominator will explode. So it will be 0, the result. And therefore, only the values of x, which are very near the point x equal to 0, will contribute to the calculation, which means that we can rewrite this integral as the limit as epsilon goes to 0 of the integral from minus epsilon to epsilon of the limit as t goes to infinity 1 minus e to the I 2tx divided by 2tx squared dx. And now we are going to use a Taylor series expansion. So actually I should call it Laurent series expansion of this complex function, this complex exponential, which will coincide with the Taylor series, but in this case we also have imaginary numbers because we have the imaginary unit. So this can be rewritten like this as the limit as epsilon goes to 0 of integral from minus epsilon to epsilon limit as t goes to infinity. And then here we have 1 minus, we will replace the complex exponential with the first two terms of the expansion, which are 1. So we have 1 plus I 2tx. And then we have other terms, but this will be smaller and smaller as x goes to 0. So if x goes to 0, we are assuming that this argument will become, let's say, small in magnitude. Even if t, remember, should be large because we are taking the limit as t goes to infinity. But we also taking the limit as epsilon goes to 0. And we are calculating this integral between minus epsilon and epsilon, which means that x will also be very close to 0. And we are assuming that t times x will be a small number, even if t is large, but we are assuming that x is becoming closer and closer to 0 much faster than t is approaching infinity. And then here we divide by 2tx squared dx, like this. And then we can rewrite this as the limit as epsilon goes to 0, limit as t goes to infinity, and then we have integral from minus epsilon to epsilon minus I over x dx, like this. And this can be written as minus I, and then we have the limit as epsilon goes to 0 and also t goes to infinity. Now let me rewrite the limit like this with these two, so only one limit, but we are actually changing notation. So I'm using this notation to denote that we have two limits. The first limit we take epsilon to be very small, it approaches 0, whereas t approaches infinity. So it is exactly the same as this one, but I'm simply using a different notation. It doesn't really matter too much. And then I have here the natural log of x to be evaluated between minus epsilon and epsilon. When I deal with complex numbers, then the integral of 1 over z, or x in this case, but in this case we have to be a little bit more careful and generalize the expression that we have for the integral of 1 over x. So in single variable calculus, when we integrate the x over x, this will be the natural log of the absolute value of x plus a constant. But when we deal with complex numbers, and we have to be more general here, so we have to assume that x can also be a complex number. This is due to the fact that we are calculating an integral where there is the imaginary unit. So we are trying to generalize our theory of single variable calculus to complex calculus. Now in this case I don't want to be too technical, but when we have complex numbers, so let's assume we are integrating dz over z, so z can be a complex number. We can rewrite this integral like this, integral of the magnitude of z, and then I have e to the I theta, and theta is the angle of the complex number z. So if I have a complex number in my plane, this is the complex number z, this complex number will have an angle with respect to the x-axis, and it will have a magnitude. So I'm going to rewrite it in this fashion, like this, also in the denominator. And then here I have integral of the magnitude of z times e to the I theta, and then I have plus I e to the I theta magnitude of z d theta, like this, and then I have magnitude of z e to the I theta, and this is equal to now integral of the magnitude of z divided by magnitude of z, so I can simplify e to the I theta here, and then I have plus integral. So the second integral here, you can see that we can also simplify magnitude of z. So I have simply I d theta. So I have the natural log of magnitude of z plus I have I times theta plus a constant if you want. But we can rewrite I theta like this, natural log of the exponential I theta. We can also rewrite it in that manner, right? And therefore we can rewrite this result as natural log of magnitude of z e to the I theta, but this is simply equal to z. So this is also equal to the natural log of z. And that's why I am rewriting this expression here as natural log of x. And you see that I'm evaluating the expression between the points minus epsilon to epsilon. So we are on the real axis in this case. And this can be written as minus I, and then I have the limit here, and we can remove the limit as t goes to infinity, because you can see that the variable t was simplified at this step when we divided t by t here. So we only have the limit as epsilon goes to 0, and then I have the natural log of epsilon minus the natural log of minus epsilon, like this. And now we can also put together the natural logs. I have minus I limit as epsilon goes to 0, and then I have natural log of epsilon divided by minus epsilon, but this will be minus 1, so also the limit as epsilon goes to 0 is really meaningless here. I have minus I natural log of minus 1, but now the value minus 1 can be written as e to the I pi, and therefore I have natural log e to the I pi, and therefore I have minus I times I pi, which is equal to pi. So this is another informal, very informal way of finding the result. And it's informal because actually we are mixing single variable calculus and complex calculus. So it's not really the proper way to do it, let's say. But it's another intuitive way to understand why the result is equal to pi, and why this function here divided by pi is equal to the Dirac delta